Okay, we'll get started. So, we're gonna add a little bit to what we did on Monday, okay? And get a little bit deeper into this. And I'm kinda assuming, okay, you know what happens when you assume that you're really familiar with the law of cosines and the law of sines and the concept of SOHCAHTOA as far as calculating angles using sine, cosine, and tangent, okay? And I'm assuming that you remember that you have those complementary angles. So if I give you an angle from the y-axis and you're gonna use cosine, you better be measuring that angle from the x-axis. Okay, do you understand what I'm talking about? Okay, so let's take a problem. So today we're gonna start off again with the remission. Okay, I have a chicken pen at my house. You know, it's got chickens in it, you know, so I can get eggs. But you know, I have a problem with my chicken pen, okay? I've got all these varmints that want to get my chickens, okay? So it's like Fort Knox or a maximum security prison, okay? Under the bottom of it, to keep the rodents from coming up from the bottom, you know, the coons and the possums and the foxes, it's got like really thick, welded wire flooring. It's really bad for a chicken to have to scratch around. On top of it, it's got a solid roof, okay? And the sides are industrial grade metal panels that prevent things from getting in and things from getting out. But the problem with it is, the roof's a little bit wider than the chicken pen, so it kind of gives it some aerodynamic lift, okay?
I see where this is going.
So I've got to tie this down, because if I don't, all of the precautions that I've taken in my chicken pen, the things that's gonna flop over, my chickens are gonna escape. Okay, and they're gonna be Sunday dinner for that possum and that coon that's out back. So I went to Tractor Supply and I bought one of those augers you put in the ground for each side of it. I'm thinking, okay, this is what I'm gonna do. Okay, and then I put another one over here. Okay. I augered it in the ground as far as I could get. I bought the really good ones, you know, they were that long, so it's really in the ground. And then I tied 2 wires to it. Okay? Now, I thought about this. I thought, hey, I can help the chickens out. They need a place to roost. Okay, so I can take the low wire and put it up about where my roost level is gonna be. Okay, slip a piece of pipe on it, set it out the other side and tie it down. And then I can put the other one up to the roof. Okay, so I've got this contraption here. With respect to the ground, this is wire A and this is wire B, okay? With respect to the ground, this one is 25 degrees above the ground, and this one is 20 degrees here, okay? Now, I've got a little meter, so I put 40 pounds of stretch here and 50 pounds of stretch there, okay? Then I decided that I didn't like that. You know why I didn't like that? Because when I opened the door to get in there to collect my eggs, it's right there where the door hits it on wire A. So I want to redo this arrangement so that I can just have one wire, a resultant wire. So how can I do that? How can I approach doing that? Because, you know, I really need to get in there and get my eggs. You know, I like a good fried egg, good scrambled egg. Cornbread needs eggs. Okay, so I need to be able to get in there. So, vector A is 40 pounds at 25 degrees above the horizontal. Vector B is 50 pounds at what angle? 45. what? 45 degrees. Above the horizontal. Okay? Now, in this great example, I'm assuming that my ground is perfectly level. Okay? And you know that is not the best case. Okay, so we've got to take this, A and B, sum them, add them, to come up with this resultant force that I know how much I need to stretch that one wire that's gonna hold that down. Okay? So we're gonna add these together. Okay, how it works today. Okay? So let's draw a free body diagram. You know that wonderful thing that you did not like to draw whenever you took physics? Okay, so let's draw a free body diagram and add those together. So we start off with vector A. Okay? Then we add to vector A, vector B. Our resultant goes from here to here. Okay? So now we've got to find this. We've got to find this. Now, there's not a 90-degree triangle. There's not a 90-degree angle in this triangle, right? So we can't just plug in a squared plus b squared is equal to r squared.
What you could do is break it up into components.
We could break it into components,
Or what's that?
or
one
we
thing?
could
Law of
use some
cosines.
other information like the law of cosines and the law of sines.
Hold on, let me find it.
So let's look at this in terms of what we know, okay? I've got a line here, so let's say I draw two parallel lines, okay? I draw two parallel lines. What do I know about lines that cross parallel lines? That the angles, which angles are which property? What do I know? That if I know this angle here is what? 25. What other angle is 25? The complementary angle that would result from this. So this angle would be 25 degrees as well, right? Agree? So what would this angle be? What would that angle be? Do we know? Okay, what do we know? 180 minus 25. What do we know about the other one? This angle here is 20 degrees plus this, so this angle is what? 45 degrees. That's a pretty sorry 45. Agree? So if that angle is 45, what is the angle on the inside? We've got 25, 25, 45, 135 would be the opposite side there, right? 135 would be the opposite side, because 135 and 45 had to be what? 180. So this portion here from the red line up is 135 degrees. So now we have 135 degrees. We have 25 degrees. So what is this angle from here to here? It's 135 degrees plus 25 degrees, which is 160 degrees, right? Mm-hmm. Agree? So now, we can find R from the relationship called the law of cosines. What is the law of cosines? The law of cosines tells me that R squared is equal to what? A squared plus B squared minus 2AB cosine of the angle of separation there, right? So all we've got to do is plug in. So we plug in and we could say that the square root of r squared is equal to r. That's math there, right? That's some high level math there. We've got that. Is equal to a squared. Well, what was a? 40. What was b? 50. Minus 2 times 40 times 50 times the cosine of
160.
160 degrees. Okay?
We have to take the square root of that whole side though.
So, how do you know what angle to plug in for cosine?
Okay. When you use the law of cosine, it's many times referred to a side angle side relation. So if I've got side A, side B, it's the angle that exists between side A and side B. Okay, so that's the angle I plug in. Good question there, because you know, you've got how many other angles? You've got a 25-degree angle, you've got a 45-degree angle, you've got a 20-degree angle. You've got a 65-degree angle. Which one do you plug in? Law of cosine says I've got to have a side, an angle, and a side. So I plug in there. Okay, so what's r equal to? Well, 40 times 40 is 1600, right? Plus 50 times 50 is 2500. So that's 16 and 25 is 4100. Minus, y'all get a calculator out and do it. Brain's not functioning like that this morning.
What kind of chicken do you got?
I've got 2 red ones and a white one. The white one is the only one that's laying eggs. And it's a fighting chicken. Somebody gave it to me. They said,
Game
hey,
bird?
huh?
Game bird you talking about?
Yeah, it's a game bird. Yeah, and she attacks every time you come in there. The other 2 just kind of look at you like, hey, what you doing here? Feed me. You know, I'm not giving you anything back, just feed me. So, but the eggs are really good for the little game chicken, you know. So, they're dyed eggs, you know, they're the small size like you buy at the grocery store. The red chickens at the jumbo size. I'm waiting on a number from y'all.
So it's 4100, and then when you do the other math, it's minus a negative, so that would be plus 3758.77. So it's 4100 plus, so 3758.77.
Then you take the square root of that, so that'd be 8800 and something. Take the square root of that.
Okay,
It'd be
I got
90
the
point
number.
something, maybe.
4100 Okay, R is approximately.
He said 88.6.
88 point something. I'm 88 point.
88.64.
That's exactly.
No. Plus a bunch more.
Plus a bunch more. Give me a few more. 88 point
64970.
664. Okay. And I asked you to do that for a reason. Okay. I hadn't worked this particular problem out, but you said 88.64. Well, the next digit was a 9. Okay, we're engineers, right? That's what we want to be, right? We want to make sure our truck drives across the bridge and not into the water, right?
So do not round down if it's
Well,
like.
we've got to think
400
about how we
times.
round our numbers. Okay, we've got to think about how we round our numbers. We haven't talked about this yet, but we've got to look at how we look at our numbers. If we're doing this and making a calculation, okay, we can take into account rounding by including some uncertainty. Okay, we can include some uncertainty here. Now, obviously, I'm picking on you, but you probably should have said 88.65 if you were going to round that. Okay, but engineering, we could write this as 85 plus or minus some percent. So 88, 89, that's 4 points, you know, 4 in magnitude. So 4 points out of 85 would be the same thing as 1 over 21, which would be about 5%. Okay, so plus or minus 5%. And we've got our error covered. Now, I know if you take a physics class or you take a chemistry class, you're using something called significant figures, and you cut your number around your number. But here, we're gonna use the percentages. So we've got 85 plus or minus 5% pounds as the magnitude of R, but that only tells us the magnitude. What else do we need to find? The direction or the angle, right? Okay, so now I'm just gonna kind of redraw my free body diagram. Maybe overemphasize some things, okay? So that I have A, B, and R. Okay, how can I find my angle? I just used the law of cosines, right? Why did I choose to use the law of cosines? Because I don't have a right triangle. If I use the law of cosines, can I not also use the law of sines? Okay, now cosine, law of cosine was side angle side. The law of sines is what? Side to an angle equals side to an angle. But in this case, if I'm looking at side B, this is the angle for B. If I'm looking at side A, this is the angle for R. And I'm gonna put A degrees and B degrees. If I'm looking at side R, this is the angle for R. So could I not say the sine of angle B over B is equal to the sine of angle R over R? And solve, just set up a proportionality. Now you're gonna say, hey, why didn't I write it this way? Is there a mathematical difference in the relationship?
Yes, because that's division. Wait a minute.
Is there a mathematical difference? No, because what are we doing? We're essentially cross multiplying, right? So does it matter if we cross multiply this way and divide by that, or this way and divide by that? No, there's no mathematical difference, okay? So can we solve? Yes, we can plug in here. Okay, we can plug in. Do we want to find sine of B? So we're going to do it this way. Sine of B, sine of angle B over B. What was B? 50 pounds?
Yes.
Is equal to the sine of, what was our angle here? 160, sorry. 160, 135 plus 25, 160. Over R, which we said was, now we're gonna actually have to go back and put our number in, 88.65, okay? Okay, so now we can solve that. So what is angle B equal to?
B is equal to 50 sine G divided.
Not everybody at the same time giving me an answer is angle B. Okay, I'll get my calculator out and plug it. You got it?
I broke it into I broke it into these components because I just find that easier.
Okay, but how did you How did you break it into its components?
I broke it into its I and J hat components.
We hadn't talked about that yet. That's our next topic. We haven't talked about that yet. So you jumping a little ahead, which is a lot easier. I'll give you it's a lot easier, but I want to show you this way first.
I got 0.1929. That sounds way too low, doesn't it?
Did you sign inverse?
11.12.
Yeah, 11.12. Okay.
Okay, so let's go ahead and.
Now, what is that angle? Actual angle. That's this angle, right? 11.12 degrees? Yes. Which is how far above the horizontal?
5 degrees?
Well, what was this angle here? 25 degrees, right? So 25 plus 11.12, which is 36.12, right? So our angle is 36.12 degrees. So we could say that this R is equal to, what did we say, 85 plus or minus 5% pounds at 36.12 degrees above the horizontal. Okay, above the horizontal. So now we've got to rewire the chicken pen to keep it from floating off, right? I'm not really so worried about the chickens escaping until they escape and get on my wife's car and leave a present and a signature, you know. Because to get up there, they're gonna leave a signature from their little claws getting up there. So, that's what I've gotta do.
This so funny.
okay, that's what I've gotta do, okay? Now, you brought up a good point, okay? There's a different way to work it. Well, what we're gonna find in most of our problems, there's more than one way to approach the math, okay? There's more than one way to approach the math. So, when we worked problems and looked at adding vectors, we did it graphically, head to tail, or through the parallelogram method, which is what we did here, okay? We can actually use something called a Cartesian coordinate system, okay? What do y'all know about the Cartesian coordinate system? It was derived, I'm not gonna use discovered, it was derived by a man in 1639, right? Okay, does anybody remember what his name was?
Cartesian.
Not Cartesian. His name was Rene Descartes, okay? And that's my example of how to use French, okay? It seems that the story goes he was laying in bed one day and he looked up and there was a fly on the ceiling. Now, why was he thinking about the fly on the ceiling? But he was thinking about the fly on the ceiling. And he thought to himself, how can I describe where that fly is on the ceiling? So he came up with a method of breaking his ceiling into little squares, like our little graph paper here, and putting a point to begin with, an origin point, at one of the corners of the room. Okay, so that he could describe the location of that fly. Now, I wonder in my mind, did the fly stay stationary or did it jump to the next square over? But, you know, irregardless, that's what he did. Okay, so he came up with this method. It's based on a coordinate system. Now, typically you look at things before this point in 2 dimensions, in X and Y. We're going to look at things in 2 dimensions and we're going to look at things in 3 dimensions, X, Y, and Z. With that, we've got to look at the relationship that exists here. All of the axes are orthogonal. What does that mean? What does the word orthogonal mean? Perpendicular to one another. What does perpendicular easily intersect or bisect by 90 degrees? Okay? Now, with the Cartesian coordinate system, it is referred to as a right-hand system, okay? What is a right-hand system? You take your right hand, okay, and you slap yourself for being in statics. But once you get past that point, you stick your thumb up, your index finger out, and your middle finger making as perfect a 90-degree angle here, here, and here. Okay? Now, rotate it. Okay? So now, if I'm looking at the board, what do I have? X, my thumb is X, that's positive X direction. Where's my Y? It's going back, that's the positive Y direction. Where's my Z? It's going straight up, that's the positive Z direction. So it's just a way to keep track of direction, okay? Now the problem is, many times since we have spent all of our life drawing X and Y coordinates, and we assume X is to the right and Y is up, when we add our third coordinate, we have to minimize. What are we doing? X and Y and Z is up. And we have to realize that that's gonna impact how we assign positive values. Okay? How we assign positive values. Okay. Now, the Cartesian coordinate system also uses something called a unit vector. A unit vector is nothing more than a directional vector or a directional component. I can't spell component. That's equal to 1. And our unit vectors are unit vector I for the X direction, J for the Y direction, and K for the Z direction. Okay? So, in 2 dimensions, that's a really, I told y'all about 4 artists. If this is a force, it has components in the X direction and the Y direction, which are represented by numbers. If it's 2-dimensional, in the X and the Y planes. If we've got an angle, we can solve for our vector. So here, F, vector F, force F, is equal to our force X in our force in the X direction times our vector I, unit vector I, plus our force in the Y direction times unit vector J. Now, F, X is equal to F cosine of our angle. Fy is equal to F sine of our angle, assuming that our angle is measured from the x-axis. And you're probably thinking, why is he saying that over and over and over? Because when you start working problems out of the book, and when you get that test question, that evil teacher that you have picks all the questions that are not measured from the x-axis. Okay, so if I have an angle measured from the y-axis, what is the x component of it?
It's going to be sine instead of cosine.
It's going to be F sine of angle. What's the y component going to be? F cosine. And that's going to slip your mind. You're not going to think, you're going to sit and think, wow, this is just plug and shove. But think about it, okay? Think about that. Okay, So, what is the cosine of our angle here? It's equal to fx over f, and the sine of our angle is equal to fy over f, right? Okay? Not a big jump there from what we've already done, okay? Now, sorry, I'll try to make it a little bit bigger. It's not gonna make it bigger. You know, the Hawaii 5 effect is gone. F is equal to the square root of fx squared plus fy squared. Okay? So we haven't really done anything different here. Okay, other than to say we can now plug in and say that f is equal to fx cosine theta I plus fy sine theta j. That's all we've done. Now, if we work the problem we worked before, what answer do we get? The same exact answer, if we plug the numbers in the right way. Okay? So, this, the Cartesian coordinate system does what? What does it do? It simplifies our math a little bit, right? It simplifies our math. But the problem we have with it is when people see I, J, and K, they kind of look at it as like, oh, those are imaginary numbers. Oh, now I've got to do an imaginary number. I can't add 2 and 2 and get 4. Now you're giving me an imaginary number? And that imaginary number is equal to 1. So you're just multiplying by 1. It's very similar and yet just a little bit different. If you took a science class and you did dimensional analysis, remember dimensional analysis, factor label? You were converting from one unit to another unit, you multiplied by a factor. What's interesting about that factor? The top number is equal to the bottom number. It may not be numerically equal, but in true relationship, it's equal. So you're multiplying by 1, because the top divided by the bottom is equal to 1. It's the same thing we're doing here, okay? Which makes it a little bit easier for us to go through that, okay? Which opens us up to now using tangent, okay? Before we were using the law of cosines and the law of sines. Now we can pull in and use the relationship of tangent, okay? What is the relationship of tangent? The opposite over the adjacent. Now, as you work through those, please make sure that your calculator stays in degrees till we get to circular motion, okay? Because then you will convert into radians, okay? And if you try to work it in radians, what's gonna happen? It's gonna give you not an answer that's supposed to be the answer that you're giving me on test, okay? So any questions on that? How are we doing there? We good on that? Okay. Let's look at components in a non-orthogonal system. What is a if orthogonal was what? Perpendicular 90-degree angles. What's the system that's non-orthogonal? It's not 90 degrees. Okay, so the axes do what? They change. Okay? They change. So, let's say, I heard y'all talking earlier about your vehicles and buying that gas that doesn't exist anywhere anymore. Okay?
Yeah, my truck no longer takes it because I deleted the flex fuel because it kept blowing the engine out.
So you're stuck on the side of the interstate, okay? And you know, you have one of those high performance cars, you know, with the bumper that's got the little square in it that you pop out and screw the little thing in so you can pull. Y'all seen those, right? You know?
Pickup truck is better.
Okay, the pickup truck's got the hooks, you know, it's
I've
got
had
the
to
hooks.
use those to pull
okay?
someone out the mud before.
Okay, so we've got this car here, okay? Now we come along and we wanna pull this car, okay? I don't know if we're stealing it, we're helping out our girlfriend, we're just gonna pull this car, okay? So, our axes are not at 90 degrees, okay? Because we're gonna tie two devices to it. We're gonna, you know, it's really stuck. It's out here on I-10, right before Goshen Van Cleve, where it drops off and it's really muddy out there. So we're gonna tie some ropes to it. And we're gonna pull in this direction. And we're gonna pull in this direction, okay? We want to calculate how much force we can exert on that. Okay, now why are we pulling it in weird directions like that? Because if you know that part of the interstate out there, it's wet from when you get off, so you've got to be a far distance, and not everybody carries a rope that far, okay? So you've got to do that. So we want to see if this is point A and this is point B, or force A and force B. We want to see what would be the amount of force we would have to exert if we called the tow truck, okay? So obviously, where's that force gonna be?
Probably about in between.
Somewhere in between. We're gonna assume that it's gonna be somewhere here, right? Not exactly, can't draw it to scale, so it's not gonna be exactly, okay? So here, the question is, find force R, our resultant force, how much we've got to exert if this angle is 15 degrees. And this angle here is 30 degrees.
Is that?
From the resultant to A?
What I'm wondering is that extra line, is that 90 from A? Is that where we've measured it, or?
I didn't say that.
I know, I'm trying to figure out.
I didn't say that. What kind of system do we have? A non-orthogonal system. What does a non-orthogonal system tell you?
Not 90.
It's not necessarily 90 degrees.
I'm wondering if you just kind of measured out, like, taking it.
What did I tell you a while ago? I'm a poor artist. And when I draw lines, they may be straight, they may be crooked, okay? But they're pointing us in the general direction, okay? We know some things. Before we ever get started, we know some things. Vector A plus vector B is equal to vector R. Right? Don't we know that? Do we also know that the x component of vector A plus the x component of vector B is equal to the x component of vector R? The y component of vector A plus the y component of vector B is equal to the y component of vector R? What do we know about A to the x? A to the x is equal to A times the cosine of our angle. A to the y is equal to what? A sine of our angle. B to the x is equal to B cosine of our angle. B to the y is equal to B sine of our angle. Assuming our angles are measured from what? The x-axis. Okay, the x-axis. Now, draw a free body diagram. how do we draw a free body diagram?
Tip to tail?
We can draw it head to tail, tip to tail. We can draw it as a point, right? Right? We can go A, R, and B. I told you I was a 4 artist. Okay? I didn't say how do we find the resultant with the free body diagram. I said how do we draw a free body diagram. Okay? Do you see the difference? Now, let's look at this problem. What is this angle? Let's make some assumptions, simplifying assumptions. That angle is 15 degrees from the negative y axis, right? So what would be this angle here? $90 minus.
Well, I'm saying, because you were assuming it wasn't from the x-axis.
But we're not assuming that, but where is this angle? This is from 15, right?
Yeah.
So now we're making simplifying assumptions that goes along that. Okay, so what would that angle be? 65 degrees from the positive x-axis and the negative x quadrant, which is the negative y quadrant, which is the 4th quadrant. What would be that angle?
75.
What would be that angle? 75 wrong. It's 360 minus 75 if you want to use cosine, right? Right? Because where's the angle measured from? All the way around, right? So what's the angle? This is 0, this is 90, this is 180, this is 270.
So it'd be 285.
285. Or we could say that a to the x is equal to a times sine of 15. I'm sorry, I'm working the wrong one. B to the x is equal to b times the sine of 15 degrees. And b to the y would be what? B cosine of 15 degrees. Now, we would have to indicate quadrants there, okay? We would have to indicate quadrants, because remember, here they're both positive, right? Here they're negative and positive. Here they're negative and negative. And here they're positive and negative, okay? So, what would our BX component be? Would it be positive or negative?
Negative.
Negative because it's in this quadrant.
Thank you.
This quadrant?
Um,
Oh,
you push button, you went up.
it's not in either one of those quadrants. It's in this one, right? So BX would be positive. Okay? BY would be what?
Wait, what?
BY. It would be a. Okay.
Wait a minute.
Okay.
The way I set it up, it's everything positive, sine positive, tangent positive, cosine positive.
And we got tangent up here anywhere.
No, that's because I'm just saying that's what's positive out of the 3. So the other 2 would be negative in quadrant 3. I thought. it'd
But
be-
we're not in quadrant 3. We're in quadrant 4.
In quadrant 4, I thought it'd be cosine positive, sine negative. just how it works out.
You're not asking, I'm not asking you that. I'm not asking you that. Yes, you are correct. If you look at it in terms of the square root of 2 over whatever, or positive and negative. But if we're looking at it here, what's happening?
Yeah.
Where's our angle measure? We measured it from this right here. Because we didn't want to plug in 265. Or whatever it was, 275. 270, 285, I'm sorry, we didn't want to plug in 285. So we've got to mentally make a note there that our value is going to be opposite of whatever value it gives us. Not that it's going to be negative or be positive. It's going to be opposite of what we give. Okay? So, can you use the law of cosines on this? No. Because you don't have side angle sine. Okay, can you use the law of sines? Yeah, because what does the law of sines relate? Angles to sides. Okay, so we can plug in and use the law of sines. Okay, so you see how it makes it take us in a different mathematical direction, but we come up with a similar answer. Okay, so think about that as we move forward when we work problems. If you just try to jump into it and use an orthogonal system, it may not work because you don't have all the information. If you could set it up as a non-orthogonal system, maybe break it into component vectors, not x and y components, but vector 1 and vector 2 in a non-orthogonal relationship, you know, it would be important. Why are you thinking, oh, it's not going to get that complex? There's a simple bridge over there. Y'all see the simple bridge? My little fake bridge there? That little fake bridge is nothing like a real bridge. And look how many members make up that bridge. Now let's imagine we want to be producing an artistic bridge.
That's a pain in the butt for Indians.
You know, and a good example of this would be, I don't know if you know what the Cochran Town Bridge is over in Mobile. It's over the Mobile River. Okay, it's the shortcut to the beach, everybody says from where I live. Okay, it's a beautiful bridge built in a curve. Built in a curve. Okay, it's not built straight up, straight down. It's built in a curve. So what happens? We don't have orthogonal relationships. We have non-orthogonal relationships. So that's your goal, to build a bridge like that before you get out of here, right?